Alright, cool. Let's get started. So, welcome to. Wait, can you guys all see me? Hear me? Yeah? All good? Alright, let's get started. So, Geotech Recap Workshop. So, this is CVEN3203. Continuation from soils, all that stuff, right? So, you guys already did like a midterm for the first half of the course, which was geology, engineering geology, all that stuff, right? This stuff is completely different. So, you get tested on week 5 to week 10, I'm pretty sure. So the topics I've kind of summarized into 4 different topics, like overall topics that you can get assessed on, right? First topic will be the bearing capacity of shallow foundations. Oh my god. Then you can get settlement of shallow foundations, power foundations, and retaining walls. So within retaining walls, what I've done, I've combined lateral earth pressure as well, right? So lateral earth pressure, there's a separate topic just on that by itself, but I've combined it with retaining walls as well. Any questions before I start off? No? Alright, cool. Alright, first thing I'm going to talk about is the bearing capacity of shallow foundation. So what is bearing capacity to begin with? I might use the whiteboard for this. So imagine you have a footing, a shallow footing. Can I see that? I don't think the camera can see, so I'll just do it on my iPad. Imagine you have a shallow footing like this, and then you've got some soil like that. So the bearing capacity is just talking about the maximum allowable pressure that the soil can take before it fails. So there's a few different modes of failure, right? We've got actually the modes of failure. I won't actually really go into too much detail, but there's something called a maximum allowable bearing capacity, right? And your job is to pretty much figure out that bearing capacity and see if your soil is going to fail or not. Okay. So there's a few ways. There's actually 2 different cases. We've got the undrained and drained version of the Hansen's equation. So this is our bearing capacity equation. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 variables. 22. Yeah? So it seems a bit scary at first. However, we can simplify it pretty easily. Right? So we have a rule where we can't use the shape factor in combination with our load inclination factor. So our shape factor is S, load inclination factor is I, depth factor is D. We can only use our depth factor with our load inclination factor only, or we can use shape factor with a depth factor. Right? We can't use all of these together. Right? We can only use some of them in combination. Right? So usually, in many cases, what happens in a question is, let's say we have to use our shape factor and a depth factor. Right? What we do is we literally just ignore everything else. We just let it be 1. So it significantly reduces the amount of variables that we're going to have to actually calculate for the question. Cool? So it's not as scary as you think. Right? It's actually pretty chill. There's a few other variables in here. We've got C dash, which is our cohesion. NC is something, it's dependent on your friction angle. Right? So you have NC, NQ, and N gamma. All of these are dependent on your friction angle. Okay. So if I scroll down a little, here it is. This is the table that's given to you in your textbook that you guys have, like a small textbook, or you guys might have the online version. But depending on your friction angle, you have your bearing capacity factors, NQ, NC, and N gamma. Another thing you have is this small expression, 2 tan whatever Greek symbol that is, times 1 minus sine Greek symbol squared. Is it recording? Okay, it is recording. Cool. This one is used in some equations down here, so you can use it for your depth factor. Is it used anywhere else? I don't think so. Yeah, it's not used anywhere else. It's usually just for your depth factor. Yeah. What else do I have to cover for something? Oh yeah, so as I said, there's 2 different cases. You've got drained analysis and you've got undrained analysis. So we know for drained analysis, our friction angle doesn't equal to 0. However, for undrained, it is equal to 0. Now, in a question, they might not just tell you straight away whether it's undrained or drained, right? But ways that they could give it to you is they could say shortly after construction or long-term after construction, right? So this is something they don't really mention in the lectures as much, but something that you should. I've like screenshotted the exact lecture slides that they have. So drained, what is that? Why is Airbnb coming up? Over here, you can see that for drained, it's long-term after construction. So it kind of makes sense that after a long time the water's going to get drained. That's how I like to think about it. Alright? Get out there. And however, undrained, it's going to be immediately after construction. So you guys can't really see. Yep, and my GoodNotes just crashed. Hey, here it is. So, for drained, you have some sort of friction angle. However, for undrained, our friction angle is just going to be equal to 0. Cool. It's not too bad. But for example, in last year's paper, and in one of your workshop questions as well, let me take a look. 2025 solutions. So there's actually a question I'm going to go through. Oh no, I'm not going to go. Am I? Yeah, I will go through this question. But they said shortly after loading and then long term after loading. Alright? So at first you're like, what the hell does that mean? Alright, well now you guys should know that shortly after loading means it's undrained, long term after loading it's drained. All good? Lovely. Cool. Then everything else to do with this question I want to explain with an example that I've got. All the examples that I'm going to go through today are just from past papers. Alright? Some of the questions that I thought really helped me prep for my finals. That's fine. Okay, let's check. Yeah. So to find these factors themselves, it's actually summarized pretty neatly in this whole table. So this first row over here is when it's undrained, then the rest of the rows is when it's drained. Okay? Undrained is a bit of an easier equation as well. The only thing that I want to really touch on later on that's might be a bit confusing is Q0 term. Okay? But I'll explain why. Now usually for NC, NQ, and gamma, if you get a weird friction angle that's not on this table, then you'll have to use these formulas over here, which I hope you guys don't have to use. It's really easy to mess up because it's such a weird formula. Cool. Okay, I guess if there's no questions, I'll just move straight into an example. Yeah, sounds good. I can't read that. I'll say 211. Cool. So the example that I want to go through is from last year's paper, as I said, 2025 question 1. So here it is. So this is the question itself. A square foundation with dimensions 3 by 3 is founded 1.2 meters below the surface of a deep layer of clay. The clay has following properties. So we've got our unit weight. We've got our cohesion. So one of them is for undrained, one of them is for drained. Then we've also got our friction angle. So again, it's 0 when it's undrained, and when it's drained, it will be 25 degrees. We've also got a uniform surcharge of 10 kPa on the left side of the foundation. All of this is, by the way, summarized in this diagram here. Alright. So we've got this 10 kPa load. We've got a what is that? An axial load of P, and we've also got a moment acting around that foundation. So one thing to note is because we have both M and N, a moment and a force acting on it, we're gonna have to account for eccentricity. Alright? It's not eccentrically loaded or concentrically loaded, whatever that word is. So we're gonna have to account for that, the eccentricity. Now, as I said, part A is asking for the bearing capacity shortly after loading, which means it's undrained. Part B is if it's drained. So I've got a diagram here real quick. So they've given us the water table as well up here. 10 kPa loading. Now this Q0 I've got on the left and the right hand side. Question? Okay. Alright, cool. Now first step, actually I'll come back to this later. First things first is my eccentricity. As something that I found out actually pretty late last year. There's two different, for our footings, we've got two different dimensions. We've got B and we've got L. Alright? B always stands for the shorter one, shorter dimension. And L is going to be the longer one. So they're both lengths, alright? But B is going to be our shorter one, L is going to be the not shorter one. This actually affects our calculations quite a lot, alright? Because if you scroll up a little, we've got B dash and L dash. If they're flipped around, it's going to mess up your calculations, alright? Cool. So eccentricity, the reason I've done B is because they both have same dimensions, 3 by 3. Alright, so if we're gonna have to reduce one of them, obviously it's gonna be the B one because B is gonna be our shorter dimension. So essentially, let me explain that again. We've got B dash is equal to B minus 2E. Alright, so we know there's gonna be some sort of eccentricity, which I've calculated to be, what is it, 0.5 meters. Now, between L dash and B dash, obviously B dash has to be the smaller one. Who's that? Oh. Hello. In fact, I'll just keep it as B, and then I guess that simplifies it down a little. So our eccentricity is going to be 0.5. B dash is going to be B minus 2E, and L is just going to stay the same. We don't have to reduce it down. Is that confusing? I don't really explain it too well, but yeah. This one here? Yeah. So it's pretty much going to be our effective length, B dash. Right? It's somewhere in your lecture slides or textbook, whatever it is. Right? But it's just a formula. Yeah. So B dash is equal to B minus 2EB, which is in the B direction. We've also got L dash is equal to B minus 2EL in the L direction. However, our eccentricity in the L direction, we're just taking it as 0. Alright, so this just, oh sorry, it should be L minus 2EL, sorry. So in the L direction, I'm just taking it as 0, so it's just going to be the same. Cool, so we've got, and then later on, whenever we're calculating area, or effective area, we're going to have to use these two dimensions here. Cool. Alright, let's quickly do our undrained analysis. So, in this question, there's no inclination factor that we have to account for. There's no, what's B? B is base factor. There's no base factor or ground factor that we have to account for. So I just let all of these be 0. SCU we do have to calculate. So we have to calculate this, we have to calculate this. CU is given to us in the question. So this is given. The other thing that it's given to us, but we're going to have to calculate it, is our Q0. Okay, so I'm going to quickly go back up to my diagram here that I've drawn. So on the left hand side and on the right hand side of the footing, there's two different pressures acting. Okay, you see on the left hand side there's an extra 10 kPa, and on the right hand side there's none of that. Alright, do you guys reckon out of the right and the left hand side, which one do we take and why? Nick? Lucky? Okay, between the, so first things first, left hand and right hand side. So Q0 left, Q0 right. they're going to be different values. Right? The reason being, over here we've got an extra 10 kPa load acting on it compared to this side. Alright? Does that make sense? Yeah. So which one do we take and why? Like in our calculation, we can't take both of them. We can only take one, Q0. But which one do we take and why? Okay, first of all, let me help. Which one's greater? Which one's less? Right hand side's greater. It would be less because there's none of the extra 10 kPa acting on it. So the Q0 acting, the Q acting at that point is going to be less compared to this side. So if you think about it, the pressure distribution sort of looks like this. Sort of. Alright, wait, let me redraw that. So it'll look like this. So there's more pressure acting on this side compared to this side. Alright? Now, so we've determined that this is less, this is greater. Now, in our actual calculation, what we're actually calculating, QU0, is the bearing capacity of the soil. Right? So would we want the greater one or the less one? What do you say? Less. How come? Exactly. Perfect. We're looking for the worst case scenario. So we're saying we're designing a footing. We're going to assume that the soil is going to be at its worst possible state. Right? So the capacity you can actually take is less than what we're designing for, essentially. Right? So over here, I've said that QU0U, sorry, there should be a U here. Is going to be the minimum of the left and the right hand side. Okay? And by the way, because it's undrained, that means there's still that water weight. It's not drained, there's still that extra pore water pressure that we're going to have to account for. So we take that total unit weight, which is already given to us as 18. Later on, when we're doing drained analysis, we're going to have to account for no, it's going to be a bit different. We're going to have to take away that pore water pressure. Okay, I'll get to that in a bit. But yeah, any questions about this part? Why we're taking the minimum? Rocky, does that make sense? Yeah. How about the front? Make sense? Over here, make sense? Sure. Yeah, and then what I've done here is just calculating my shape and depth factors, which hopefully I don't have to explain. Just plug it into the formula and you'll be alright. Now, plugging that into the QU formula, you end up getting 303.95 kPa. However, the question is actually asking to determine the factor of safety. Okay, so I'm going to go back to my notes really quickly to find the here it is. So sure, we can find QU. However, the factor of safety itself, I don't have it in my notes for some reason. Where'd it go? Okay. No. Okay, I don't have it in my notes for some reason. But the way to pretty much calculate it is you're gonna find the force acting on your footing and then divide it by the maximum allowable force that you can take divided by what's actually acting on it. Okay? Hello. So we've got, this is going to be our maximum possible force that it can take. So this is going to be the effective area times QU, which is going to be our bearing capacity. And then from there, QU divided by P. P is what's actually acting. So we've got P, they've taught us, is 1000. And then yeah, from there you can find your factor of safety. Honestly, I don't think they actually mentioned this stuff in the lectures. It's too much to do that. I don't know, I don't really watch the lectures, but I would say that having this in your notes somewhere is pretty important. How to figure out your factor of safety. I think I might have skipped over it when I was making my notes, but it's very useful to have. I think they mention it in a lot of the workshop questions as well, how to figure it out. Yeah. By the way, the workshop questions are really, really good to prep for the finals, in my opinion. I really, really like them. They help me the most because, especially for the retaining wall question, it was literally exactly the same as the workshop question that we got. Yeah. Anyways, part B. So everyone cool with undrained analysis? Yeah. So now we're going to look at drained analysis. So drained analysis, we've got this huge equation here. Okay. So I've already crossed out the factors that we don't need because we're only using shape and depth factor. All right. Now what we're going to have to find is NC, or pretty much everything that's not crossed out. Oh no, this is given to us as 10 kPa. This is also given to us because we know we're going to use this submerged formula, 18 minus 9.8. Oh, that's our effective unit weight over here. Everything else, so this, this, and this, and this, we're going to have to figure out. B dash is given to us. Not given to us. We actually calculated it earlier to be B dash is equal to 2 meters. Q0, we're going to have to do the same thing as earlier, except there's a slight difference because our unit weight actually changes. Alright. So first of all, our n factors. So for 25 degrees, we've got 25 degrees. We've got these values here: 20.7, 10.7, 6.8, 0.31. So we're just plucking out for, numbers from a table. Cool. Hopefully I don't have to explain that too much. Pretty chill. Next, we've got our factors. All right, SD factors. So SC, if I scroll up a little, because we're no longer up here, we're not in the undrained section anymore. We're in the drain section. So SC is equal to this, SQ is equal to this, S gamma is equal to this. We're going to have to find all of them. Another thing we have to be careful of over here is because our depth is going to be equal to 1.2. So we know that D is equal to 1.2 meters, but our B dash is equal to 2 meters. So we're going to have to use this formula over here. No, wrong one. This one up here. Top formula. Because our conditions say so. Similarly, we're going to have to use this one up here. And this is just always 1 for all friction angles. Scrolling down. So that pretty much summarizes, that's wrong, that should be 1. So that summarizes all of our factors over here, right? Any confusions about this? No? Chill. The thing I want to explain is this, the Q0. So as I already discussed, we're going to take the minimum from the left-hand side and the right-hand side. Right? The only thing that changes is this value here. So this is equal to 18 minus 9.8 kilonewtons per meter cubed. Because there's no more water, so there's going to be that excess. No. We're going to have to minus that pour water pressure. Okay. So we just take the minimum, and everything else is just subbing in. Okay. So all of these crossed out factors I've just taken it as 1. Right. As we know, you can't take shape factor along with inclination factor and depth factor. So it's just, you have to pick. I think I just went over the rule, but here it is. Do not use shape factor in combination with load inclination factor. Use it with depth factor and load inclination factor only. So D or I. And the other one is going to be S and D. Cool. Not too bad. It's a bit scary at first because it's such a huge equation, but when you kind of understand what's going on, it's actually really recent. Yeah.
So how do you pick these up?
Sorry? Oh yeah, so by the way, I should probably explain that. So in the question, they haven't given us anything to do with inclination. I'm trying to think of an example where that was. 2019 paper.
Okay, so yeah, so it'll be pretty obvious in the question.
Yeah, it'll be obvious in the question. I hate it. So for example, this is the 2020 paper. You see how there's that proposed excavation thing? That affects our G's, which is our ground factor or something like that. Everything else, if there's an inclination, that means our soil is like at an incline, something like that. Base factor, they cover in the textbook. I actually don't know, I'll be honest. But yeah, from the question, you'll be able to tell. Actually, let me take a look. You can kind of take a look at your formulas as well. So this thing is if there's like you have a footing like this, but your ground goes off like that, something like that, I reckon. Then your inclination factor might just be if your footing is at an incline, I'm guessing. And then your base factor, I'll be honest. I just don't know. I've never used the base factor, I've only used the ground factor. And then shade factor and depth factor.
So if it's on an incline, maybe it's got like funky shape.
So funky shape.
Or is it like ugly shape?
I doubt there would be something like that, I'll be honest. I doubt it. But I'll be honest, I'm not actually too sure myself. I think yeah, just have a read through your vector side of the textbook. Do I have it anywhere? I don't think I have it anywhere in my notes either. Here it is. Oh yeah, so definition of parameters used in the table above. So base factor, so your base factor is when your soil is at an incline. If there's any excavation, then you'd have to use the ground factor. Inclination factor, I'm actually not too sure.
When loads act on the normal.
Oh, so when it's loads acting at an incline, might be. So for example, if you have like a footing like this, and then you have loads acting like that, that might be the inclination factor, yeah. Yeah, then you've got two different cases for sloping ground and horizontal ground, yeah. Interesting. Cool. Alright. So to finish off this question, we have to figure out the factor of safety. So again, you find QU, capital QU, which is the force, which is the maximum force you can take, and then you divide it by what's actually acting, which is 1000. So this is my factor of safety. So as I said, this thing, it's not really explicitly mentioned anywhere, so I suggest you write this down. P is the load acting on the footing. Right. So this isn't applied, it's already applied. And then QU is going to be your max load it can take. Cool. Let me see if I'm still recording. Lovely. Any questions? Alright, cool, lovely. I'll quickly move on to settlement now. So settlement, the good thing about settlement is like most of it's already covered in soils, right? There's only a few things that change a little bit. So I'll go to my notes to explain this. So settlement, there's three different parts to settlement. We've got our initial settlement, initial/immediate. Then we've got our C, which is our primary/consolidation settlement. And then S is our secondary / our creep settlement. Three different parts to it. Our first one is initial settlement, which is pretty easy. There's just two formulas for it. So it can either be a strip footing or a rectangular footing or a circular footing. Right. So I don't really have to explain this in too much detail. Q is going to be the pressure acting on it. Right. The kPa. You've got your Poisson's ratio, Poisson's ratio, and then the only thing that's weird is the mu1 and mu0. So mu1 and mu0 is something you're going to have to find from these tables down here. Okay. So the good thing about this is that they actually give us a little diagram as well, which is really, really nice of them. But you're going to have to find two ratios, L on B, H on B, or three ratios, and as well as D on B. So over here you're going to have to find L on B, D on B, and H on B, and that'll allow you to calculate your two mu factors. Yeah. Similarly over here, I'm not sure what this Greek symbol is, but I'm going to call it mu. No, I'm going to call it m. Similarly, you're going to need H on R and D on 2R. So you need H on R and then D on 2R. So you need to calculate two things from it. I actually haven't seen circular footings anywhere. You might see it in like a workshop question or something. I'm not sure. It's probably worth doing it. But I haven't really seen it around. Now for layered soils, there's actually a bit of a method to figure out your settlement. So let's say you've got sand and then you've got clay. Okay. If you want to find the settlement of just the sand itself by itself, you're gonna have to find the settlement overall of including the sand and clay, and then minus the settlement just due to the clay. Alright. So sand plus clay, you're gonna have to use this whole height to the bottom of the layer, the rigid layer. The clay, so this is clay and this is sand. The settlement just due to the clay itself, we can calculate the immediate settlement using this equation up here. And then this one over here, similar thing, except the immediate settlement, we have to take that whole distance there. It's a bit weird. There's like an example in the lectures that they explain it really, really well. I'm not bothered, I'll be honest. I'm gonna go through a different example. The next step is our primary / consolidation settlement. This thing is exactly the same thing as soils, right? So you've got to find your change in vertical stress, change in delta Z, sigma Z. So there's a few different cases. You've got your concentrated point load, where you can just use this. You've got your uniform live load. You've got your strip footing. You've got your circular area load for a circular footing. Then you've got your rectangular area load, which, if you guys recall, Fadum's chart. And then you've got irregular load, but they won't ask you this. Alright, that's using Newmark's chart, which is like really weird. But you have to put the shape on the chart itself, then count the number of squares, but sack that. Then you're not going to ask. This is pretty common. The question I'm going to go through actually uses this as well. So I'm going to go through it with the example. Then you're going to have to find your initial and final effective stresses. And then, depending whether you have normally consolidated or overly consolidated, you've got different equations. Okay? Trust me, like this PC value, I think they give to you, so it becomes a bit simpler. I think in soils you have to calculate it yourself, I don't remember. But once you find, I'll just explain it with an example. Yeah. Blah blah blah. That's your final consolidation settlement. Then you've got, as a function of time, so you've got your average degree of consolidation, your TV, CV, all that stuff, and then you can use this graph to figure out TV and that. Right? Same thing as soils. Then the third part of your settlement is creep, which is time dependent. So you've got your time of interest, and you've got your time that it takes for your primary consolidation to finish, and you've got a factor as well. This factor, they'll give it to you. I hope they give it to you. Yeah, because I don't know how else you would calculate it. Alright, cool. That's pretty much the settlement part of, what is it? Shallow foundation. So I'll go through an example really quick, then I'll give you guys a short break after that. Settlement of shallow foundation. So this is the question that I'm going to go through. A soil profile at a site is given where our footing is 4 by 5 meters, and it's to be constructed at a depth of 1 meter below ground level. The footing carries a load of P equals to 10,000 kilonewtons, and the water table is 5, okay, blah blah blah, whole bunch of that. You've got 2 layers, sand and clay. Calculate the settlement of the footing due to deformation of the sand layer only. So we've got sand layer up here, okay? So this is the layered soil thing that I was talking about. However, in my previous example that I was talking about, over here, we had sand down here and we had clay up here. Okay, so the settlement of the sand is directly correlated to the deflection, the settlement of the clay. Right. However, in our case, because sand is this top layer, we don't really have to care about the settlement of the clay. Right. We literally just straight use the immediate consolidation formula, and we can find the immediate settlement formula, and we can find the settlement just in that clay layer by sand layer by itself. So this is just due to the sand only. Then they ask for the long-term settlement of the rigid footing due to the consolidation of the clay. It may be based on 1-point estimation. So I'll explain what that means in a bit. First part though, sand layer only. We've got this formula, as I showed you earlier, for a rectangular footing. So if I'm taking a look at it as a top view, let's say this is 4, this is 5 meters. First thing I'm gonna ask you guys, I'll tell you guys, so there's like a point load acting right at the center of, what is it, 10,000? 10,000 kilonewtons. 10,000 kilonewtons. Right? If I wanted to convert this into a area KPA, or like a pressure acting over the area, all I got to do is divide it by the area that's acting on. Right? So what I've done down here is going to be 10,000 divided by 20, because it's 5 times 4. So our Q value is just going to be 500 kPa. Any confusions about that? No, makes sense? Good. So that's the first thing. B is the second thing. That's going to be the smaller dimension of our footing, which is what? Smaller dimension of our footing? 4 meters. Perfect. Alright. Poisson's ratio, they give it to us as 0.3. All we have to do is find mu0 and mu1. So what I've done here, I figured out h of b, l of b, and d of b. So for mu1, I'm going to use these first two. H over b is 1, and then L over b is 1.25, which is like somewhere in the middle here. So 1.25 over here, and then 1. The intersection we get is 0.5 to be our mu1. Cool. Oh, I've done it 0.45. Okay, I'm gonna change this up. Give me a sec. H is the distance between the base of the footing and the rigid layer. Okay. So for example over here, I've taken H, the next layer, yeah. So I've taken it as 4. These I'm only calculating it for the sand. Right, if I was calculating it for both the clay and the sand, then I would have to take this whole thing here. Does that make sense? Yeah, good. Then I've done the same thing for mu 0, which I actually forgot to write. Mu 0 is equal to 0.95. Cool? Yeah. Sub that in, you end up getting your sediment of the sun. 9.725 meters. Seems like a lot, actually.
So sand doesn't have progress in there.
Sorry?
Sand doesn't have consolidation.
Oh, well, in this case, they've... Oh, why haven't I done the... Oh, I forgot to do the rest. Yeah, okay, so there should be the... There's no creep in this case, they haven't told us to creep. But the other consolidation, primary consolidation, we'll have to actually figure it out as well. Why haven't I done it? Let me see why. That's interesting. Definition of the sand layer only. Yeah, okay, I reckon it's only 5 marks, I don't think you have to do all that. I'm thinking because... Sorry? I reckon you probably have to... I'll check. I'll come back to it during the break, but check if... SC. So I'll check if there's a consolidation sediment. I just skipped over it fully. Okay, anyways, part B. Calculate the long-term sediment of the rigid footing due to the consolidation of the clay layer only. It may be based on a 1-point estimation at the middle of the layer under the center of the footing. So if you think about it, footing like this, center of the footing, we're going to take a point below the center of the footing, midway through the clay layer. So midway through the clay layer is here, right, which is 5 meters below the footing. So I'm going to scroll down a little. What I've done here is I'm using Fathom's, the 1 point base estimation, right, using Fathom's chart. So I've split it up into 4 because they've taught us that take it based off the center of the footing, right, directly below the center of the footing. NZ is going to be equal to half of this dimension, which is 2 meters, and then MZ is going to be 2.5 meters, 5 divided by 2. However, because Z is equal to 5 meters, we can just say M is equal to 0.5, N is equal to 0.4. The way we got that is because we know it's going to be MZ over Z. MZ is going to be 2.5 over 5, which is 0.5. Similarly, same thing with N is going to be 0.4. Any confusions? Cool. Now, from here, so we've got N equals to 0.4, M equals to 0.1, 0.2, 0.3, 0.4, 0.5, 0.5, and the intersection of this gives us an influence factor of 0.007. 0.07, sorry. Cool. Now the other thing we can calculate from here is going to be our change in stress. So over here, I'll quickly explain it. So the change in stress, they've given it to us as Q on IR, but because we've broken up our footing into 4 different sections, this equation only applies to one of them, right? So just this part here. So to find it for the whole footing, we've got to multiply by 4. Cool. That's just going back to soils. So essentially our total change in stress is going to be 4 times Q times IR. Q is going to be 500 as we found earlier. IR is 0.07, which we just figured out, and then multiply by 4, we got 140 kPa. Cool. Now the next thing we're going to have to find, so step 2, if I scroll down, step 2 is going to be find initial and final effective stress. Our initial effective stress, I'll quickly explain it. So we're trying to find the effective stress at this point here. True. So it's going to be the unit weight of sand times 4. No, sorry, times 5, because we take it from the top, times 5 plus the unit weight of clay effective times 1. The reason we take the effective unit weight is because it's under the water table. Okay? So it's submerged. So that's what I've done here. I've done unit weight of sand times 5 plus 1 times whatever we have here. Okay? Does that make sense? Which you end up getting 94 kPa. And the final effective stress is going to be that plus the change, which we knew as from earlier is 140 kPa. Lovely. Alright. So now, another thing they've also told us in the question is that the something pre-consolidated, post-consolidated, I don't know what the P stands for, PC, sigma PC, which is 220, okay? Therefore, because we know that initial is going to be 94, final is going to be 234, right? That means this falls in between these two. Yeah? Hopefully that's not too hard to understand. Because of that, our change in E formula, so our change in E formula is we're gonna use this one. Okay? So CC they've given it to us, CR they've given it to us, we've calculated this, we've calculated that, this is also given. So everything that we needed in the question is already given to us. Alright? So scroll back up, CR given to us, CC given to us. What we have to do now is just plug in our numbers. So this is 220, this one is 234, 94. And then you end up getting change in E is equal to 0.0045. And finally, to find the consolidation settlement itself, plug it into the formula. Actually wait, I've got to explain what H0 actually is. So H0 for this case is, we're going to take it as 2 meters here, because H0 stands for the depth of the clay layer, right? Because what we're trying to find here is the settlement of the clay layer. So it's going to be the settlement, it's going to be the total height of that clay layer. If it was going to be for the sand, then I'd have to take 5, for example. Right? If this was 3 meters, then I'd have to take 3 meters. But in our case, it's 2 meters. Cool. So this is going to be clay layer. This is also given to us, by the way, in the question. E0. Yep, they've given it to us here, 0.5. So everything that we need is given to us, plug it in, and get 16 millimeters as our consolidation settlement. Okay. In terms of the other one, Lockie, I'll have to check. Yeah, this one. I'm pretty sure you don't need to calculate it because...
Yeah, it's because it's sand, drained.
It's drained, right?
Yeah, so
you don't have to. Right. Let me actually write that down here. So, could you repeat that real quick? So, don't...
If it's sand, the consolidation of creek are negligible.
Sand.
Yeah, in sandy soils, almost all settlements occur immediately after application, and therefore immediate settlement is the most dominant settlement
Gotcha.
with the sandy soil.
So SC and SS, secondary. Alright, no, okay, I knew there was reason. Thank you. Some sand. Cause it's sand. Okay, there's something to know. Very good point. Okay, everything else makes sense. Yeah, cool. Any questions? What I'll do, I'll give you guys like before I move on to pile foundations and retaining walls, I'll give you guys like a quick 10-minute break. If you guys have any questions, you can come up to the front, or just relax, and then I'll come back. Let me pause. Alright, cool. We get started again. Before I do continue, Designs brought up a pretty good point. Alright, listening. One thing, it kind of makes no sense for it to be 9 meters. Alright, it's a bit ridiculous. It should have been 9 millimeters. And the reason for that is over here I've taken 80 MPa. It should be MPa. So in the thing, they've given it to us in MPa. So it's like a matter of minutes. Yeah, I kind of messed it up. It shouldn't be meters. It should be millimeters, I think.
Start the recording.
Yeah, I've started recording. Thank you. I remembered this time. Cool. So now I'm moving on to pile foundations. So I'm going to go through my notes really quickly. So in piles, so I'll actually go through. Where it is. So piles, we've got our floating piles and we've also got our end-bearing piles. So floating piles are just piles that just float in the soil, right? Their main form of capacity comes from friction between the pile itself and the soil. We've also got end-bearing piles, which keep going down until they hit a really strong soil or rock, right? That's where the main, I guess, capacity comes from. For single piles, what we look at in this course is either ultimate capacity or settlement, or both, right? Ultimate capacity kind of varies between cohesive and cohesionless soils, right? There's two different formulas that we cover, okay? Settlement, you've got your floating piles with a rigid layer underneath. So that looks something like this. So let's say this is my pile. Shit. And then with a rigid layer underneath is like somewhere nearby we've got like a rigid layer. Okay? If it's just a floating pile, then we usually just ignore that. Maybe the layer is like somewhere down here, really far below. It doesn't really affect our capacity or our settlement. And we've also got our end-bearing settlement as well. Now, pile groups is a bit of a different one. So the ultimate capacity you can calculate in two different ways. You can find this capacity of one single pile and then multiply it by the number of piles you have, or you can consider the whole pile group as a block. So let's say you've got piles like this. Alright, so you've got these piles over here. So you can consider them separately, then multiply by 4, or you can consider it as a whole block. So you can consider it like this. Like a cube, or a rectangular prism of some sort. Right. The question I go through doesn't actually cover it, so I'm going to go through like a different example really quickly just to cover that group thing. Alrighty. So ultimate capacity, this is our general equation. you've got your shaft capacity and you've got your base capacity. So shaft capacity is the capacity due to the friction of the between the shaft and the soil. Then you've also got your base capacity, which is just due to your base of the pile. Right? For cohesive soils, as I said, there's two different formulas, one for cohesive, one for cohesionless. Right? So cohesive is undrained strength, which when you summarize it, you end up getting something like this. Alpha Cu times AS, which is the area of the shaft, plus CUB times N-CAD. All of this stuff is in my notes here. So you've got N-C CUB, which is just the cohesion at the bottom of the pile. Alpha, you've got this table. It's just a reduction factor, not a table, a graph. And yeah, that's pretty much it. It's just one formula there. Another formula that you have is for cohesionless soil. So you're actually given this table in your textbook. So based off your relative density, you've got different values, whether it's going to be driven or bored, cast in situ, you've got different values. Okay, I'm going to explain them with the example that I have, how to use this table. And this average vertical stress is a bit weird, but the question I have explains it as well. So I'm going to just delay it, explain it with the question. And yeah, this is your ultimate capacity of a pile if you have a cohesionless soil. Okay, not too bad. There's a bunch of formula at the moment, just a bunch of formulas. Yeah, all you got to do is find them separately, sub into the formula, and happy days. Sediment, as I said, you got floating piles. You got your piles equation, P-I-L-E-S, piles. Your I is your influence factor, right? Your influence factor also depends on your pile stiffness factor, which has another formula here. Alright, so this is going back and forth between formulas, graphs, this, that, then plugging it in. Floating piles with the ridge layer underneath, same thing as earlier, except you have a RH multiple, which you would have to figure out from this graph. End bearing piles, same thing, MR comes from here. AP is going to be the cross section of your pile. Yeah, that's right. Then pile groups, as I said earlier, you've got the minimum. Oh, okay, as I said, you can calculate them separately. So you calculate each pile, multiply them together, or you can take an entire block. Consider it a block failure. Alright? What you're going to have to do is take the minimum of both of those. I'll quickly go through an example after. So I've already got an example in my notes here. I can probably find a better example though. So then you've got more sediment equations, blah blah blah. Yeah, this is piles. It's probably one of the easier topics because all you have to do is jump through between tables, graphs, and then you just plug it in. Those are the three things that you do. Alright. Let's go through this question. This is from the 20-something paper, I don't know. A 15-meter long steel pile is driven, so that's a key word, driven, 14 meters into the 20-meter layer of sand, another key word because it's cohesionless, right? Which overlays bedrock. See figure 3. This is my figure 3. So we've got a few properties that is given to us. We've got relative density, Young's modulus of the soil, we've got friction angle, and we've got our total unit weight. Now, not really cool actually, but something interesting about this question is that they've given us a hollow pile, okay? Because they've given us a hollow pile, the base, strength of the base, you can just ignore because it's hollow. The only thing that contributes to strength is going to be the shaft, right? Sure, you can kind of include this small area, but it's so negligible that you just ignore it, right? So, Let's take a look. So, because it's cohesionless, I'm going to use this formula here. And as I said, relative density is 85%. Therefore, it's counted as dense. 0.85 falls within that range. And another thing they also told us is that it's driven. So scrolling down, we're going to use this part here. Driven and driven. Cool. So my F value is going to be 1.5. My NQ value is going to be 180. Make sense? Now, so I've pretty much figured out this here, that's F, and I've also figured out NQ, 180. Now, the thing I have to figure out now is sigma V dash, which is my average stress, and I've also got the stress at the bottom, effective stress at the bottom of the pile. So what I've done here is I've drawn a stress diagram, effective stress diagram, like that. Like that. So how did I get these values? So at the top here, we can see that after 5 meters, we've got like a change in unit weight due to the water table. So they've already told us for the sand, the unit weight is 20 kilonewtons per meter cubed. So this vertical stress at this point is just going to be 20 times 5. Do you have to explain that? 20 times 5? No? It's just unit weight times 5. Now, over here, because my unit weight changes, it's now going to be 10.2 because it's under the water table. So I'm doing 20 minus 9.8. My unit weight is, I'm just going to take it as 10.2 now. Multiply that by 9. This is 9 meters here. And you get your effective stress at the bottom, which is 191.8. Essentially, this is just equal to 100 plus 10.2 times 9. Cool? Okay, lovely. So we found the effective stress at the bottom. How do we find the average effective stress? There's a few, last year there's like a few ways to actually calculate it. But I think the correct way is this way. So I actually used to do it differently. I used to find the force. I actually don't know. I don't remember how I used to do it. But I'll show you guys the correct way to do it. So what you guys got to do is find the area of this entire thing. That gives us, I guess, the total effective stress, and then you got to divide it by the length that it's acting over, which is 14 meters. So over here, this part is just the area of this triangle. So 5 meters divided by 2 times 100, area of that triangle. And then next I found the area of this parallelogram. Trapezium, which is 9 meters divided by 2 times 100 plus 191.8. Alright, high school formula, I'm not going to explain it. But once you find that total, you divide it by 14 meters, and you get your average effective stress. If you don't understand it, don't worry, just know how to do it. Okay? Just memorize it. And yeah, we know that AB is equal to 0. AS is going to be the area of the shaft. So there's a formula for it, pi dl. Pi d being our circumference, multiplied by the length that is covered in the soil, or embedded length, essentially, which is just 14 meters, and you get AS being 22 meters. When you sub this in, you should get a PU of, that's wrong. Let me calculate it again. 22 times 111.65 times 1.5. So it should be, that's wrong, should be 3684. I'm just going to take 3684.5, and then PA is just going to be PU divided by 3, I get 1228.2. And that's my answer. Any questions? Trixie? Make sense? Yeah, not too bad. Hey, before I move on to the settlement part, I'm gonna go over like a block failure kind of question. 2022, I think, had a block failure if it opens. I just lied. No, it doesn't. 2021. Here it is. So very similar kind of question. So in this case, it's actually cohesive soil, not cohesionless. So the formula is a bit different here. So for a single pile, I found the maximum capacity per pile, right? And we've got in total, I think, 4 piles, 4 circular concrete piles. So the group capacity is just going to be 4 times the single one. And then I also have to figure out the block as well, the capacity of the block. So block failure, what I've done, I've just taken it as a huge block, and I'm treating this as like one big pile, essentially. Right? So alpha for this block failure is going to be 1. Cu is just our cohesion. Cub is going to be the cohesion at the bottom, which is the same. N-C is a factor that I've calculated to be 8.43. And area of the base is just going to be 3 squared. Area of the shaft is going to be 10 times 3, which is 30 times 4, because I'm going to take it on each side. Okay. So the shaft is on all 4 sides. I have to account for it. So what I've done essentially is, because this is greater, I'm just going to take the minimum one, which is what I calculated above here. Okay. Makes sense? No? I've kind of gone through this really quickly. I haven't really explained it because for this one, it's asking for the allowable bearing capacity of the pile. So PU, same thing as earlier, except it's a group now. It's a pile group. So what I did earlier was find it for a singular pile. Right? Now I'm calculating for a group. So for a group, there's two things you're going to have to account for. So, or 2 ways you can actually figure it out for a group. Do number of piles. Can you guys see that? Number of piles times capacity of single pile. Or you can do a block failure kind of way, where you just treat it as a block. What I'll do actually, I'll go through my notes. So over here, this isn't my solution, this is Henry's solution for a question that has block failure incorporated into it. So you can find it for a single pile and then multiply by the number of piles, which in this case is 9. Or you can treat it like a block, and because it's for a block, the special case is where alpha is just equal to 1. Oh, I think that might be because it's clay. Yeah. So there's actually a special case for alpha. I'm not sure if I've got it in my notes. Oh, here it is. It's right here. So alpha is equal to 1 if it's clay. Right? That's a special case. But then all you got to do is, I guess, treat it like one big pile. You've got the shaft capacity, you've got the base capacity. You add them together and you get your overall capacity. And then between those two, you're gonna have to take the minimum value. You take the minimum value, why again? Worst case scenario. Exactly. You take the worst case scenario. Alright, you guys can take a look at this in your own time. Where was I? There's also some settlement Again, this isn't my solution, this is Clarissa's solution. Some old head. But yeah, I'm going to continue with this question over here. Part B is asking us for the vertical sediment of the pile if it's subjected to a load of 2,500 kilograms. So, floating pile, in this case we have a floating pile with a rigid layer at the bottom, or a rock, which is a bedrock. So, if I go back to my notes, I'm going to be using this formula here. Piles times RH. Okay. So P is given to us as 2,500. L is just the length of the pile, which is 14. ES is the elastic modulus of the soil, which is 100. I is the influence factor we're going to have to calculate from this graph. I have not provided. Oh, here it is down here. This influence factor. RH is also something we're going to have to calculate from this graph. Cool. Let's go through it bit by bit. So RH depends on the values of LD and L over H. So L divided by D is going to be 14 divided by the diameter of the pile, which is 0.5 meters. L over H is the height of the clay layer, of the layer. So they actually provide us with a diagram here. There's a rigid base here. From the top of the soil to the bottom of the soil is our H. L is just going to be the length of the pile that's embedded into the soil. So L divided by H in our case is going to be, L is 14 meters and H is 20 meters. So 14 divided by 20, 0.7.
Why is H not from the base of
Well, that's what the diagram says.
because it's hollow?
No, not because it's hollow, it's just what the diagram says. So over here, it starts from the top of your soil layer, goes to the bottom.
So they always provide vertical.
They should, yeah. If not, then I don't think you can even do the question. Well, in this case, it's an end-bearing. No, it's not end-bearing. So it's got a rock rigid layer underneath. So you're gonna do that 20 meters. If it was like just a floating pile, I don't think they'd provide you with that because you don't need it. Right? In this case, you actually need it. Cool. So RH, I'm just gonna use this thing. This diagram's really weird because you've got H on L and you've got L on H. So it's just H and L are the values up here, 1, 2, something. L and H are these values. It's so weird, this diagram. I don't know why they don't just provide L and H, but anyways, L and H we know is 0.7, so 0.5, 0.6, 0.7. 0.7, and then the other value is 28. So 28 falls somewhere in between 10 and 25. I've got that wrong. Sorry. It should be between 25 and 50. So it will be somewhere here. So you get like 0.8-ish. Yeah, 0.8. 0.78, close enough. I'll just keep it at 0.78 for simplicity. I don't want to go around changing my answer now. But close enough. Alright? You don't have to be exact, as long as you guys can show your understanding in the exam, you get the marks. Now, the next thing we have to calculate, so we've got RH, so we've got P, we've got L, we've got ES, we've got RH, now we just need I. Okay? So, going back to my notes really quickly, for I, we're going to be using this graph, which depends on your pile stiffness factor K and your L and D value. Okay, L and D we've already calculated, I'm pretty sure, to be 28. My pile stiffness factor follows this formula here. So EP is the elastic modulus for the pile, ES is for the soil, and RA, if it's a solid pile, it's going to be equal to 1. If not, then it's going to be less than or equal to 1. So it's pretty much just a ratio of your area like what we have. So in our case, it's just going to be something like this. That's an oval. So something like this. So RA is going to be equal to AS over AG. So area of the solid divided by area of the gross. So gross area is just going to be this whole thing, right? Oh, area of the soil. Sorry, area of the soil is just going to be this inside part, I'm pretty sure. No, that's not right at all. It should be this part here. Okay? And the way you calculate that is the sum way. Yeah. So we know this inside part over here, this inside diameter is 0.45. This outside diameter is 0.5. So you just minus the areas from each other. So it's going to be 0.5 squared. So in reality, there should be a pi on 4 here as well. Pi on 4, pi on 4, pi on 4. But because they all just cancel out anyways, I've just ignored them. So this cancels out, this cancels out. This can piss off as well. And your RA value becomes 0.19. So overall, my pile stiffness factor is 380. I'll give you guys a minute to observe. If you have any questions, let me know. Kind of get into your brains. Any questions? It's a bit of a lengthy step, but it's not too bad. It's not too hard. Like, it's rinse and repeat. You do more questions, it becomes easier and easier. Alright, all the workshop questions are really, really good for pilots. Right, I think. Okay, so we've got 380, which is like somewhere here. So this blue line represents 500, I'm pretty sure. So 380 is somewhere here. And I'm looking at an L on D value of 28, which is somewhere between 25 and 50. So I'm just going to take it around here. This is going to be my influence factor, which is 3. If there's any problems with this, let me know. I'm not sure if I've done this entirely correct, this graphing part. I'm pretty sure I have though. But yeah, I've got an influence factor of 3. So going back to the top of the question, now I have everything I need. I've got P, I, L, E, S, and RH. All I've got to do now is plug it in. So this is P, this is I, this is L in millimeters. I've done it in millimeters because I've got my E in MPa. Okay? And this is my RH. So you end up getting 4.18 millimeters. And this is my total sediment. Cool. Look how cool this is, by the way. Right. Present me. I can go to the class. Okay, it's not fucking up. I've got Trixie. I've got Jen and Hi. Yo, it's not turning. Oh, it's at maximum. That's it. Yeah, I think I just broke it. Yo, work, please. No, it's not working. Hold on. Who else do we have here? We've got the AC. No, that's not the AC. That's a projector. We've got my brother. And we've got our front people. Tough. We've got me. We've got the wall. Let me pan it down a little. We've got design. And we've got with Lucky. lucky. Who's next? And it's also got auto tracking, so if you move, stand. Oh, never mind. Does it work? Oh, it does work. Yeah, it's tough. Anyways, back to the class. Class 4. Alright, cool. Let's get back to it. Yeah, that's powers, whatever. Retaining walls now. So retaining walls, the thing about retaining walls is that the questions are always so similar. Right? From the workshops to the questions, past finals, they're really similar. So there's two kinds of retaining walls that we can take a look at in this course. You've got this one, I forgot what it's called, anchored retaining wall, and then the other one that you have is like the gravity retaining walls, like this, something like that. Can you guys see? Yeah. In this case, it's a bit different because in this case you don't have to take into account the self-weight of the retaining wall. Out of this one you do have to. So there's a weight here and there's also a weight here. Weight 1, weight 2, but I want to discuss. On top of that, if you have some sort of soil on top of this edge, so that's your soil, you're going to have to take into account the pressure of the soil in this part and also the gravity of the soil here as well. As well as same thing over here, whatever. Workshop has a question like that, I think. But the one that I'm going to be focused on today is this one. This is similar to what we got last year. But yeah, before that, I'll go through a bit of theory to do with retaining walls. So your global factor of safety and your failure modes, you've got 3 different kinds of failures. You've got sliding failure. So this is for a gravity retaining wall. You can get sliding failure or overturning failure. For the one that I'm going to go through today, just like that one very thin retaining wall, I don't think you can get sliding failure because you can't really slide. The only thing you do is like turn about this point here or overturn. However, it's still good to check sliding failure. I think you still get marks, right? If you don't check it, you lose marks. Yeah, anyways. Partial factor of safety, this is in line with the standards AS467A. There's a few factors that you're going to have to account for. You've got your load factors. So depending on whether your soil is active or passive, it either reduces your load or it increases your load. I'll get to that in a bit. Then you've got your soil reduction factors, whether it's drained or undrained. And you've got your structural classification factor. Let me get rid of this. Then on top of that, this is the lateral earth pressure thing that I was talking about. They cover it in like a whole week of content. Do you guys know if you guys don't get tested on Coulomb criterion, more Coulomb? Or is it just rankings too? You could get it? Yeah. Oh fuck. Okay, so I haven't prepped anything for that because last year they told us that it's only going to be rankings theory.
2 years ago,
Did they test it? 2 years ago? 2020 something. Okay, anyways. Okay, that's interesting. So you could still get tested on more Coulomb. I don't have anything prepped for that, I'm sorry. But I'll just go through rankings theory for today. But honestly, the steps are going to be the exact same. The only thing that changes is how to find your K values here, KA and KP. After that, it's exactly the same. So the only step that's different is calculating KA, KP. Calculating and checking everything else, like your forces, your moments, everything like that, is still going to be the same. Okay? So, we're taking a look at an embedded wall design here. By the end of our calculations, what we want to check is this thing over here. So what this is pretty much saying is you've got some sort of factor, structure classification factor. You've got your resisting forces, and you've got your disturbing forces. No, you've got your resisting forces and you've got your disturbing forces. What you want is your resisting forces to be greater than your disturbing forces. That way, the structure is going to be safe. If you imagine it, whatever's being applied, you can resist it. Right? So the disturbing force is getting resisted. That's what we want by the end of it. Cool. So the question that I am going to talk about, actually, quickly going back to this. So your load factors, you'll see you've got dead loads, water pressure, and your live loads. Your water pressure isn't really affected at all. Factor stays 1. Live loads do change a little bit, so you're going to multiply by 1.5. However, for your dead loads, if it's going to be an active pressure, you have to exaggerate it. You have to multiply by 1.25. Okay? Again, the reason for that is covered in like your week 5 content. It's pretty much saying that you want to exaggerate what's actually acting on the structure, but you want to kind of do the opposite for how much you can resist. That way you can have like an extra safe structure. Right? And then over here, this is like your passive pressure. Right? Passive pressure kind of contributes to that resisting factor, so we're going to reduce it. Okay? Make sense? Cool. Right, might as well just go through a question then. Let's take a look. So figure 4 shows a section 5 meters high of a 5 meter high anchored retaining wall embedded 1.5 meters into the ground. Because it's sand, your cohesion is going to be 0. C is going to be equal to 0. So if I go back to my Rankin's theory here, you've got something that that includes cohesion. That's just going to be, oh shit, I just spat everywhere. That thing's just going to be equal to 0. Okay? You've got your total unit weight, you've got your friction angle, water table, they've given that to us in the diagram here. But they've told us that you may assume the total unit weight of the sand above and below the water table is the same. So the total unit weight isn't going to change. Yeah. Use Rankin's theory of lateral earth pressure to determine the active and passive horizontal stresses from points 1 to 6. And they've also told us assume in situ soil conditions. So in situ soil conditions comes into play for this part here, your load factor. You can see they've told us it's in situ soil. Oh, sorry, not your load factor, your soil reduction factor. If it was a different class, then we'd have to use a different value, obviously. Alright. Cool. So first things first, my load factors. Step 1 is my load factors. So I've got to exaggerate or de-exaggerate my soils. I'm not sure if that's the right word. Antonym of exaggerate is thinking. You gotta understate. Tough. Okay. So you gotta understate your. My laptop's just bugging right now. Hold on. So you gotta understate your passive pressures, right? But you gotta exaggerate your active ones. So active ones, you multiply your forces. Passive ones, you reduce them. For your Q, so by the way, this is something that's mentioned in your textbook. If they haven't given you a load up here, you've got to always assume a 5 kPa load, right? Like even if they don't tell you. So this is how the question came. They didn't give us a 5 kPa load, but they've told us to assume a 5 kPa load up there. Okay? That's just a rule. That's how we design retaining walls. So our active sand unit weight, this is going to be 1.25 times 18. Our passive sand is going to be 14.4. So our passive pressures come down here. All of our active ones are over here. Okay. So active comes to the right essentially, passive from the left. Next thing we're going to have to do is our soil reduction factors. So go to my notes. We have sand, so we're going to use this top part. And they've told us it's in situ soil. So for our phi u phi. Okay. And for UC, we've got two different values. We've got 0.85 and 0.7. 0.85 and 0.7. So I actually haven't included this one in my working out because we don't need it. Because our cohesion is just equal to 0. We use these up here. So UC, to find our effective cohesion, right? We just multiply that factor with our cohesion. Because our cohesion is just equal to 0 anyways, we can just ignore it. So what I'm going to do, I'm just going to ignore this because we don't actually need it. What we do need is this factor here, which, because they've given us a friction angle of 35 degrees, so we're just going to have to plug this into our calculator, pretty much where this is 0.85, this is equal to 35 degrees. I think that's correct. Tan inverse in degrees, 0.85 times tan 35, 30.76. That's correct. Okay. Any confusions? It's pretty much just following the steps now. It's like a cookbook, just follow the steps. Now, this is where the Rankine theory comes up. So, Ka, if I scroll down, our active coefficient is going to be tan squared of 45 minus, I've actually forgot to include it here, this is going to be effective. Our effective angle, friction angle, divided by 2, which when you plug this into your calculator, you get 0.323. And something a bit nifty about Rankine's theory is just Kp is just equal to 1 divided by Ka. So instead of going through this process again, all I can do is do 1 divided by 0.323 to get my Kp. Okay? And as I said earlier, my effective horizontal stress follows this formula, Ka times sigma v dash minus 2c squared of Ka. And because it's sand, the c is just 0. So all I have for my question is just this part here and this part here, which I've noted down here. Here it is. So this is my Ka. This is my Ka. Cool? Yeah? Lovely. So, I forgot what's next. Oh, okay. So, we can figure out our vertical stress diagram, right? But what we need is our horizontal stress diagram, right? So pretty much what I'm going to be doing is converting this thing to help you with that. Something that I found pretty useful is to actually draw up a table. Right? Instead of doing each of the points separately, drawing up a table actually helps quite a lot. So this is a table that I like to draw up, something like this. So I've got my 6 different points. So the points that I'm talking about here are the red ones. We've got 1, 2, 3, 4, 4, 5, and 6. Those are going to be our 6 points. You can notice that one of them's above the water table here, and one's below. Okay. So I've got all my vertical stresses. So I'll quickly explain how to do that. So first of all, you can just figure out your total vertical stress, and then to find the effective one, as you guys know, we know that effective stress is going to be equal to total minus U. This is from soils. Yeah? So, let's take a look. At the very top here, at point 1, the vertical stress is going to be 5 times 1.5. 1.5 because of this load factor that I have. Cool? Make sense? No? No response? Make sense? Yeah? Does that make sense? Rocky? Nick, get off your phone, mate! Cool. 7.5. Then at point 2 over here, we're going down by 5 meters. So the unit weight of sand here is, because it's active, it's going to be 22.5. So it's going to be 22.5 times 5. 22.5 times 5 plus 7.5, which you get to be 120. Hopefully that makes sense. Yeah? And essentially the vertical stress at this point is going to be the same as well for point 3. Point 4, we're just going to have to include that extra bit. So I've got all my vertical stresses. The pore water pressure doesn't actually take into effect until point number 4. So at point 1, 2, and 3, there's no pore water pressure, because the water table starts at this point here. Alright, it actually takes into account, alright, even at point 6, there's no pore water pressure. It's only at point 4 and 5. Okay? And then to find my vertical effective stress, I'm just going to multiply it with minus that from there. No, minus this from this. Yeah. And then you eventually get your effective stresses. Right? Now to find my horizontal effective stress, I'm going to multiply my Ka value. Okay? So Ka, or it might be Kp. So because up here it's active between points 1 and 4. So 1, 2, 3, 4, this is all active. Right? Then over here we have passive. Okay, so for point 5 and 6 is going to be passive. 1 through to 4 is going to be active. So over here, just a note, is going to be Kp times V dash. Okay. So let's quickly figure this out. So we've got this being 0.323, so 7.5 times 0.323 is 2.42, times that by 120, 38.76, 44.91, 6.9 times 3, yes, 21.360. Any questions about that? No? Cool. Now the last thing we're going to have to do is to find the total horizontal stress. We're going to have to add our pore water pressure. So it doesn't actually take into effect until $59.61, $36.36, and 0. Let me quickly check if these values are correct. Yeah, okay, looks correct. Okay, yeah, looks correct. Yeah, lovely. So, this is what my stress distribution is going to look like. So, at the top over here, I've got 2.42. Then at point, this over here, I've got 38.76. Then next one is going to be 59.61. And then I've got 36.06 over here. That is what my stress distribution looks like. Horizontal stress distribution, not vertical. Any questions about that? Nah. Lovely. You guys seem a bit tired, but I'll try to quickly go through this last part, okay? So, now, the second question, they're telling us to find the ultimate tension force of the anchor, okay? Assume the retaining wall is to be constructed in a high risk area. where failure would result in significant damage or loss of life. That last part over here is where the structure classification factor comes into play. Because they've told us failure results in significant damage or loss, we're taking a look at structure type 1. So our phi u value is going to be equal to, before all of this, is going to be equal to 0.9. Okay. Next thing we're going to have to look at is, from our horizontal stress distribution, we're going to have to find all the forces acting on the retaining wall. So the way to do that is, I'm going to break it up. So I've got this block over here. So I've got a force acting in the middle like that. Then for this triangle over here, I've got a force maybe acting here. Let me break it up into colors. Then down here I've got another block. Let's do it in blue. I've got another force here. Then in red I've got this force here. Then finally in green I've got this passive force here. I've got this force here. Cool. So I've got F1, F2, F3, F4, F5. And then I've also got that TD force where, let's see, I can, over here, TD. Okay. TD is coming from here, 1.5 meters below. So in terms of forces, we've got a few active forces. We've got F1, 2, 3, and 4 being active. 5 and 6, or TD, is going to be our passive. So I'm going to say F1, F2, F3, F4, F5, and TD, minus TD. So all of these passive, active, and these ones over here are passive. Passive slash resisting, active slash disturbed. Okay, so this is going to be S star, this is going to be R star. Cool. Let's actually calculate these forces really quickly. So TDs are unknown, we don't know what TD is. F1 is going to be this force here, 2.42 times 5. Which is 12.1. So I'm just taking the area of this distributed load. Oh, actually, who does environmental here? Is it just Nick? Yeah, this is something we cover in engine mechanics, so if you don't know, looking at the camera now, just let me know later. Just message me later about it. I can try to explain it, but I don't have the time right now. Then F2, we've got this triangular force, so I'm going to say 38.76 minus 2.42, that's going to be that distance here, or that pressure, multiplied by 5 divided by 2, because it's a triangle. So 38.76 minus 2.42 times by 5 divided by 2, 90.85. Hey, you know what? I'm just going to take the values from when I did the question, just to save a bit of time. 2020. Okay, but these are our values for the forces. I'll quickly explain how to go through these forces. So this rectangle over here, you just calculate the area of that rectangle to get the force. Same thing over here, you calculate the area of the triangle, then divided by 2. The only thing that might be confusing about all this is the lever arms. So I'm going to quickly go through the lever arms and how to actually calculate them properly. So for force 1, we're taking all these lever arms with respect to the point O at the bottom of the retaining wall. So it's going to be this, we know this force is acting halfway in between these 5 meters. Alright, so this part is 2.5, and we know this part down here is 1.5. So 2.5 plus 1.5, you get 4. That's going to be our lever arm, 4 meters. So this is with respect to point O. WRT with respect to 4 meters. And the reason we need this lever arm is to actually calculate the moment. Okay. F2 for this triangle over here. This part over here is actually 1/3 of the length, so it's going to be 5/3 plus 1.5. 5/3 plus 1.5, you get to be 3.17. F3 is just going to be 1.5 divided by 2, 0.75. So 1.5 comes from here, and then I'm just dividing that by 2 to get that distance here. Then this one's going to be 1.5 divided by 3, 0.5. So 1.5 divided by 3. Cool. Lastly, F5 is just going to be the same, 0.5. And then this one, we can actually figure it out. 5 minus 1.5, oh, it's going to be 5 meters. So because we've got 1.5 meters here, 1.5 meters here, so the distance between here and here is just going to be 5 meters. Cool. Any questions? Alright, cool. I'm just going to speed through this really quickly. Now the moments, I'm just going to multiply them, 48.4, 90.85 times 3.17, 287.7, 58.14 times 0.75, what the fuck, 43.6, 15.64 times 0.5, 7.82, 27.015 times 0.5, 13.5, and then this is just going to be minus 5 TD. Let me quickly check. Yeah, beautiful. So everything that we have up here is going to be S star. Everything down here is going to contribute to R star. Okay. So the formula that we actually have, so let's say first of all, sum of forces in the X direction. Sorry. So we've got 2 different kinds of criteria to check. We can check sliding, and we can also check overturning. So my sliding check, I'm going to need that phi times R star has to be greater than or equal to S star. But this is only to do with my forces in the X direction, or like sum of forces. Right. So my resisting forces, I've got 0.9 times 27.07, 27.015 plus TD has to be greater than or equal to 12.21, 12.1 plus 90.85 plus 58.14 plus 15.64. So what I can do is I can rearrange for TD. Therefore, TD is equal to 12.1 plus 90.85 plus 58.14 plus 15.64. Answer the bracket. 169.35. Yeah. 169.35 keys. Any qualms, any questions about that one? Nah. Cool. Now, we're also gonna have to check overturning. So same formula, except it's related to moments. So we've got 0.9 times 13.5 plus 5 TD greater than or equal to 48.4 plus 287.7, 43.6, 7.82. So TD is going to be equal to 48.4 plus 287.7 plus 74.53. That's extremely wrong. One sec. $83.42. Again, going in this direction. Okay. Wait, hold on. I'm about to finish up really quick soon. So we've got two different values for TD. Which one do we take? One's bigger, one's smaller. Which one do we take? I actually don't know myself. Let me check. I forgot. Let me check. You take the maximum. Cool. Here it is. So, another thing to know, by the way, these forces that I've calculated are per meter. I forgot to explain this part, but these are all per meter. So first of all, we take the maximum, which is going to be 169.35. And to calculate the total force, we take the length of the rod so at 2 meter intervals. So the inserted depth of 1.5 and at 2 meter intervals. So we got to multiply by 2. So I multiply this by 2. We get 169.35 times 2. 338.7, and that's your final answer. Right? So I kind of rushed that last part because you got some more people coming in. But yeah, we'll end it there. If you guys have any questions, I'll still be in this room. Just let me know in a bit. All right, cool. Thank you. Why do we take the large value? Great question. Let me think. So if you really think about it, TD is a resisting force. I think it's because they've taught us to determine the ultimate tension force. It's going to be like the maximum tension force for the anchors. Another reason I could think, well, the main reason I took the maximum is because that's what the rockets did. So I don't really know, I'll be honest. You guys are disturbing. No, TD's passive, it's a resistant force. Because what's going on is all this sand is pushing on the retaining wall, causing it to like flop this way. But that anchor is pulling it back, so it's a resisting force.
So the passive force is just the anchor. Yeah.
Alright, cool. Anyways, just take the maximum. That's what the workshops do. I don't have explanation for you guys. So, yeah. Thank you. Yeah, I'll end the recording there as well. Oh my god, I had the camera on the whole time. Oops. Okay, that's fine. They can probably see this one.